Okay guys, still on our Jamb 400 chemistry series. Are you ready with me? This is our part 5. Let's rock it together very quickly. We are going to be looking at question 41 all the way to question 50. You know we are heading to 400 questions. That's why it is called Jamb 400 series. So 400 questions that they revolve around in chemistry. And you must take this very tight and very, very serious. Are you ready with me? Let's go. First and foremost, look at question 41. The question is, which of the following separation techniques, that means this question is from where? Separation techniques, right, is extensively employed in the Gary processing industry? Anywhere you hear the word Gary processing, you don't need to think it twice. You should know it straight. Is it your filtration, or it is your crystallization, or it is your sieving, or it is one we call your what? Your distillation. Very simple, easy, and direct. Gary processing is not filtration. No, that's what sieving. Sieving is the correct answer. That means option was C, the answer. So you see these 4: filtration, crystallization, sieving, distillation. They don't play with them. So let me take you around them very, very fast, so that anywhere you see them, you know them to their core. I've treated everything from beginning to the end about separation techniques. It's already in chemistry and chapter 2 in the app. So you can go and rock through it very, very fast. So let's look at it very quickly. First and foremost, the first here I want you to note, right, is that in the Gary processing industry, sieving is an essential step. Right, it is using separating the fine Gary particles from the coarse ones. So it's based on sieving. It's a principle that works based on the particle sizes. Are you getting it now? And don't forget that there are various steps in Gary processing. There are 7 of them. Number 1 is called peeling and washing. When you carry your cassava, you need to what? Peel them. That cassava tuber, you need to peel them. After you have undergo peeling, what will you do? You wash them. Those of you that grew up in the village and you have seen how those things are done, you know exactly what I'm saying. Step 2 is grating, right? What happened in the grating? The cassava is grated into what? Mesh, right? Where they will mesh them. Are you getting it now? And then the next is fermentation. You need to allow it to undergo fermentation. Are you getting it? Why are you allowing cassava to undergo fermentation? Because it contains cyanide, and this cyanide is toxic. Better listen. The grated cassava, what happened to it? It is fermented for a few days. Why are you fermenting it? To remove the cyanide from it. So why is it that it's not advisable to go and carry cassava like that and just boil it and start to eat it? No, because of the presence of what? Cyanide. So fermentation is what we take out the cyanide from it. But there are some cassava anyway that some people boil and then they eat like that, but it's not all. Take note, what are you removing there? Cyanide. Number 4 very quickly is called pressing. That fermented mash, right, is pressed. Why are you pressing it? To remove excess water from it. So when you remove, the reason for pressing is to remove the water. That's why they will now place like heavy things on top of it to remove the heavy water from it. After that, the next thing is sieving, right? So the cassava mash is what? Sieved. That's where sieving is coming in now, to separate fine particles from what? Coarse one. Are you getting it? And this step ensures that the Gary has a uniform texture before you start carrying out your frying. So the reason why sieving is done, right, is based on the particle sizes. And then number 6 is frying. That's where they now start frying it in that local crude method. Of course, there are big machines that they use in processing these things nowadays. So the sieved mash, right, is roasted in hot pan, right, to become dry, and then you now form that whether it's Jebu Gary, depending on the location you are, right? There are different kind of Gary, but Jebu Gary is very, very popular all over Nigeria, right? So it will give you that crispy Gary vibes that you need, right? And then another thing is final sieving. That one is optional. You may choose to do final sieving, or you may choose not to do final sieving, and then you now start packaging it, more like soaking it. As the case may be, you now enjoy yourself from there. So don't forget, why must you ferment cassava? So as to remove your cyanide that is toxic or poisonous in the body. Does it make sense? Figure that very quickly with me, please. Another is filtration. What happened in filtration, right? Because they brought it as an option, so you must know filtration to the core. What happened there? In filtration, it is used to separate a solid that is insoluble in liquid. So what you need filtration for is solid that is insoluble. That means it will not dissolve, right, in the liquid. What do you carry out there? Filtration is what you carry out. And don't forget that this method rely on the difference in the physical state and the insolubility of one component in the other. That one is jam pass question direct. filtration rely on the difference in their what? Physical state and the insolubility of one component in the what? In the other. And don't forget this, that mixtures that are separated by filtration, what are the good examples of mixtures? Number one is suspended particles in what? In your liquid, like your mud water, right? Mud water. But most of the time, you carry out like decantation for mud water, where you allow it to settle down, right? And then you decant it from it. Another very quickly is sediments in water. When there are sediments in water, you carry out filtration in it. And then another is your saturated solution with undissolved solid. What do you carry out there? Filtration is what you carry out in that. If you get that very quickly with me, please, like not to forget this. Take note of it too, and don't forget that when using filtration, the pure component we want is called the residue, and that residue is what is left on the filter paper. Now look at your normal filtration experiment. What happened in your filtration experiment is very simple. What happened is that you can see that you need your beaker, then your filter funnel, and then your filter paper, right? And then you are turning the mixture that you have into it, and then as you are turning it into it, what happens is that you're now seeing droplets of those things that are trying to gather downwards, right? Beautiful. Now from this, there are three things you must pay attention to. Number one is called the filtrate. So the liquid only is what we call the what? The filtrate. When you hear filtrate, what is it? Liquid only. The one that will remain inside the filter paper, what do you call that? It is called the residue. What is it called? Residue. So residue is what is left in the filter paper. Why that liquid only that will go down, right? Through the funnel. That one is called the what? The filtrate. Shall you remember the two? Shall you remember the two always? To get that very fast. Another is called crystallization. What happens in crystallization? Very simple. It's a method of obtaining or forming what? Solid crystals from saturated solution without completely evaporating the solvent. Why? Because the crystals you want to obtain, right, they decompose on what? Heating. So what happens is this. Look at it in crystallization. This is how your crystallization setup is like. Are you getting it now? You have your beaker, right? You have your beaker. You have your soluble solid in solution, right? That's the saturated solution. You are bringing in your tripod stand, your Bunsen burner. You're going to heat this guy here. As you heat it, so that the water will evaporate. As the water evaporates, not everything will evaporate totally, and then you now carry your pan, right? And then you now spread that saturated solution around it, so that it will do what? The water can eventually do what? Escape. What you're going to have? You're going to have pure crystals at the end of the day from it. Are you getting it now? So crystallization is used because that sort you are trying to obtain the pure crystals of it. It decomposes on what? Heating. Does it make sense? Get that very fast with me. Please don't forget, in crystallization, this is the question they always revolve around. The question says sugar is separated from its impurities by. This is the major question under it. Anytime you hear sugar is separated, how do you obtain sugar? Sugar, is it by distillation, or by evaporation, or by precipitation, or by what? Crystallization. What's the answer? Crystallization is the answer. Does it make sense? That one is very simple, easy, and direct. Why? Because sugar will decompose on heating. That's why you don't use evaporation to dryness from it. For it, what do you use? What do you better use there? You better use what is called your crystallization. If you get that very quickly. What about distillation? In distillation, what happens is that it is the process where a liquid, right? A liquid, for example, in distillation, what you need is what? What happened to that liquid when heated? So you need to what? Heat the liquid. What will it change it to? It's going to change into what? Vapor. So a liquid when heated changes to what? Vapor. Are you seeing it? Now that's distillation for you. And the vapor, now this vapor, what will happen to it? When cooled. When you carry out cooling in it, what will happen? It will form the liquid again. This is called your distillation. So distillation is reversible. What is distillation? It is a process whereby a liquid when heated changes to vapor, and the vapor when cooled forms the liquid again. That's called your distillation. Does it make sense? And don't forget that simple distillation is primarily used to recover the pure solvent in a liquid solution. What do you want to obtain? Pure solvent. If you forget these things, I go nod you. And don't forget this, that the principle of separation is based on the difference in their boiling point. Why do we use distillation? It works with the principle of the differences on their boiling point. Are you getting it now? The constituent mixtures. That is, the solvent has a lower boiling point than the what? The solute. So what do we use there? Distillation. Like your Eva water, your Ragolis water, all these guys. What do? Distillation. And don't forget this, that simple distillation can be used to obtain pure water. Pure water. Water is a universal solvent. That's why we call it either pure water or pure solvent. From a sample of water from sea, right? For example, you have your sea water. You want to obtain pure water from sea water. What do you use? Distillation, right? Whether it is water from your river or from your well or from borehole, you want to obtain pure water. What do you apply there? Distillation is what you apply. If you get that very quickly with me, that means you have done very well. Look at how your distillation look like, right? You need your heating compartment, which is the Bunsen burner, right? You need your distillation facts, you need your temperature, your thermometer that you use to check the temperature of it, right? And so on and so forth. You need your receiving flask. That's all. So this is how this guy look like. If you get this very quickly with me, that means I'm good to rock. You see, and these things I'm explaining, you must know it to the core. I know they play with you. If you get that very fast, let's look at the next question very quickly. Right, one important question before we go to the next that they always ask under distillation. Let me give it to you. Look at the question. Pure solvents are obtained by. How do you obtain pure solvents? Hold on a bit very quickly. This class you're watching right now is just one out of a series of classes within the LearnLift app. And guess what? LearnLift is a mobile app, right, where you study intensively as well as extensively. So within the LearnLift app, you can see it very quickly. You have access to all your subject there. You have your use of English, you have your mathematics, you have your physics, you have your chemistry, you have your biology, you have your Jamb 400. All of them, they are different subjects within the LearnLift app. And of course, you have different topics under every particular subject, and everything has been narrowed down to you, down to the curriculum, with their past questions and everything to the core. And don't forget that within the LearnLift app, you have access to your video lessons, where you can start going through your classes uninterrupted. You have access to your notes. Oh yes, your notes, well organized, well structured for you, and you are running through all of them. And of course, inside the notes are past questions for you. You have access to your past questions in CBT format, where you can go through all of them extensively well. All of it within the LearnLift app for you and more. And guess what? Very important. You want to download the LearnLift app, all you need to just do is head down to Play Store or your App Store and type LearnLift. That's all. Once you type LearnLift, of course, the app is going to pop up for you, and you're going to see the logo, and then you download the app, and then you follow up on your studies intensively. Before we proceed, let's get back to class. Flow with me. Is it by distillation or by condensation or by your extraction, or it is by your evaporation? What is the answer? Distillation is the answer. What? A. Pure solvents are obtained by what? Distillation. These ones are bonus questions you should know. Now that you get that, let's look at question 42 very quickly. We are going all the way to 50 in this particular class. In question 42, the presence of common salts as an impurity. Common salts as an impurity in water. So if you add common salt, right, to water, that salt we add as impurity in the water. It will cause the boiling point of the water. So what will it do to the boiling point of water? Anytime you add impurity to pure solvents, what will they do? Option A say it will be the same. The boiling point is going to be the same. It's not true. It's never going to be the same. Option B say it's going to be 100 degrees Celsius. It's not true. It's not going to be 100 degrees Celsius. Option C say the boiling point is going to increase. Option D say boiling point is going to reduce. The answer is between your. This cannot be the answer. The answer is between C and D. If you add impurity to a solvent, what will happen to the boiling point? Will impurity increase boiling point, or impurity will decrease boiling point? What is the answer? Of course, impurity will increase boiling point. Option C is the correct answer. This question is still from chapter 2 in the Jamb, in the syllabus, in the app. Go to the apps, chapter 2. I've treated all of these things to the core. Are you getting it now? Now listen to this. Let me explain. First and foremost, under the factors that affect the purity of substances, there are certain things you should know. What are the factors that affect purity of substances? Very quickly, there are 5 factors, 5 of them. Number 1 is called density. Number 2 is called freezing point. Number 3 is called melting point. Number 4 is called boiling point. And then number 5 is called refractive index. All these 5 properties affect the purity of substances. Please take note of this very quickly. Hence, impurities have great significance on them or great effect on them. Are you getting it now? So impurities, we have effect on density, freezing point, melting point, boiling point, and what? Refractive index. Very quickly, let me explain it. On the grounds of your density, what is density? Very simple. Density is your what? Your mass per unit volume, right? And the symbol for density is your what? Your rho in physics, which is mass over volume. Don't forget this, that the density of a pure substance is definite and constant. So your pure substances, their density is definite, it is constant, right? It is same. While that of impure substances is higher. So what does impurity do to density? Impurity increases density. Don't forget to. Another thing very clear you must know is this. For instance, the density of your pure water, right? It is what? Your 1.0 gram per watt cm cube at 4 degrees Celsius. Now, if you add impurity to it now, it will be greater than 1.0. Are you getting it? Number 2, very quickly, is the effect of freezing point. What happened there? Take note that the freezing point of a substance is the temperature at which it transitions from liquid to what? To solid. You are moving from liquid to solid. That means you are freezing. Now, what happened there? Please, impurities. Freezing point is transitioning from liquid to solid. I beg you, impurities will decrease. Impurities will what? Will decrease or lower the freezing point of any pure substance. Impurity will decrease or lower their freezing point. Hence, we call it freezing point depression. What will impurities do? Impurity will depress, lower, reduce freezing point. Are you getting it now? And don't forget this, that the freezing point of pure water is what? 0 degrees Celsius, right? Beautiful. While water that contain dissolved salts, right, they are going to freeze at a temperature that is below 0 degrees Celsius. So if they now go below 0 degrees Celsius, maybe they are now going to minus 4 degrees Celsius. Now, what is the cause there? Impurities have come in there. Are you getting it now? Beautiful. If you get that very quickly with me, that's that's anomalous expansion of water. Anomalous is between your 4 degrees Celsius towards to 0 degrees Celsius. 0 degree. It's not minus 4 degrees Celsius. Don't be minus 4. Sure, you get it now. This one is not anomalous. That one, I mean, we treat it with you in physics. So get that very quickly with me. Another is called your melting point, right? Beautiful. So what will happen in melting point? Don't forget that melting point is the temperature at which a substance transitions from solid to liquid. It is moving from solid ice block. It has turned to water. Melting. Are you getting it? Don't forget that melting point of a pure solid is sharp. Melting point of a pure solid is definite. Melting point of a pure solid is within short melting range. Yay. And don't forget this very quickly, that the melting point of pure sodium chloride is what? 801 degrees Celsius, right? Now, what will impurity do? Impurity will lower the melting point of a solid and widen the melting range. For instance, if something has a melting point of, let's say, for example, melting point is, let's assume that we have it to be 92 to 93 degrees Celsius. What will impurity do? Impurity will come and widen it, right? Beautiful. So impurity can come and start it from like 85 now, right? To probably like 93 degrees Celsius. That's impurity for you. So what will impurity do? Will impurity lower melting point or impurity will increase melting point? Impurity will lower. Impurity will lower. It will lower melting points. What will impurity do to freezing point? It will lower freezing point. But when you now come to boiling point, it's a different thing entirely. Does it make sense? Don't forget it very quickly, that the boiling point, right, is the temperature at which your liquids transition into gas. The temperature at which your liquid, they transition, boil now. Normal liquid have changed to vapor, gas. That's boiling point for you. Don't forget that the boiling point of a pure liquid is sharp. Your pure substances that have not been contaminated, they are sharp, definite, or short range of what? Boiling point. But when you now bring in impurity, you have spoiled everything. But first, look up. The boiling point of pure ethanol is what? 78 degrees Celsius, right? While that of pure water is what? 100 degrees Celsius at atmospheric temperature and what? Pressure. But now, when you bring impurities to it, impurity will raise, or impurity will elevate, or impurity will increase the boiling point of your what? Your pure liquid, or widen the range of it. Listen, what will impurity do? Impurities will elevate boiling point. Impurity will increase boiling point. That's why we call it your boiling point elevation. Freezing point depression, boiling point elevation. All of it is all thanks to what? Impurities. Does it make sense? This is where they revolve around in that area. Together very quickly with me. What about refractive index? You know already, refractive index is how much light is bent or refracted as it moves from one medium towards another medium, right? That's refractive index for you. And don't forget that the presence of impurities can alter what? Refractive index. Does it make sense? If you get this very quickly with me and you are very, very sure you understand it to the core, that means you are good to flow into the next. Again, for the last time, don't forget, what are the factors that affect the purity of a substance? There are 5 of them. Your density, your freezing point, your melting point, your boiling point, your refractive what? Index. And don't forget this, that for pure substances, all these factors, if they are pure, if that substance is pure, these factors are what? Kept what? Constant. They are kept precise, they are kept fixed and within narrow range, right? Beautiful. But when you introduce impurities to it, it will affect the overall performance of everything. That's all. If you get that very quickly with me, let's look at this question. Question all the way says the electronic configuration of an element E. And then they gave us the element, right? They say the element is, first and foremost, you need to count and then know your 2 here. 2 plus 2 is how many? 4. 4 plus 6 is how many? 10. 10 plus 2 is how many? 12. 12 plus 6 is how many? 18. 18 plus 1 is how many? 19. Which element is number 19 in the periodic table? That's potassium, right? Potassium is what? Number 19 in the what? In the periodic table. Now, the element is A, halogen. That's not halogen. Halogen, they are in group 7, right? Option B say is an alkaline earth metal. That's alkaline earth metals are the group 2 elements. The group 2 elements are called the alkaline earth metals. The group 1 are called the alkali metal. Potassium is in what? Group 1. Alkali metal. Sodium, number 11, is in what? In group 1. Your lithium is in what? In your group 1, right? Hydrogen, helium, lithium. Your lithium, your sodium, potassium, they are in group 1, right? Beautiful. Now, option C say, as a stable octet structure is not true. It is the group 8 or the group O element that have stable octets or duplet what configuration. And then option D say it is an alkali metal. That's the correct answer. Option D, alkali what metal. Does it make sense? Group 1 elements alkali metals, group 2 elements alkaline earth metal. Alkaline earth metal. The group 1 elements alkali metals. Abi, the group 7 elements are called the what? The halogens. In fact, I've given you from group 1 all the way to group 8 or the group O. What you call the other name, group 6 are called the chalcogens. I've given it under your periodic table, right? Beautiful. If you get that very quickly with me and you understand it to the core, look at the next question. Question number what? 44. Are you ready? The question say a salt which loses mass, salts that lose mass when exposed to air. When you expose the salt to air, it will lose mass. That salt is option A, hygroscopic. Option B say deliquescent. Option D say efflorescent. And then option D say what? Fluorescent. First and foremost, fluorescent. That one is totally out of the way. First, yeah, right? It is either between hygroscopic, deliquescence, efflorescence. Efflorescent salts, right? What happen? They lose water of crystallization. And because they will lose their water of crystallization, what will happen to them eventually? They are going to lose mass. So efflorescence, these are salts that will lose mass at the end of the day because they are always ending with dot something H2O, dot X H2O, right? Whether pentahydrate, decahydrate, as the case may be, they are the one that will lose mass eventually. You must know efflorescence, deliquescence, hygroscopic. I've explained it in part 4, right? This is part 5. I've explained that already in part 4. I'm not going there. But please don't forget what is the answer to this option. What C is the correct answer. Again, don't forget to very quickly that when you hear efflorescence, what happens? Efflorescence is the process whereby a hydrated salt, what will happen to it? It will lose water of crystallization, whether partially or completely, to the atmosphere. And we say such hydrated salt. If you hear hydrated salt, it means it has water. Such hydrated salt is said to be what? Efflorescence. Are you getting it? It's said to be efflorescent. And don't forget there are examples of your efflorescent salt. Number 1 is your sodium carbonate decahydrate. That's your sodium trioxocarbonate for what? Decahydrate, Na2CO3 dot what? 10H2O. Another is called your copper 2 sulfate pentahydrate. That's your copper 2 tetraoxosulfate 6 pentahydrate. So this guy can lose all the water safe. Are you getting it now? Another is called your what? Your iron 2 sulfate what? Heptahydrate. Are you getting it now? These guys can lose their water of what? Crystallization. Again, I like you to know this, that efflorescent salt, they lose weight. Why must they lose weight? In fact, they will not just only lose weight, they will lose their crystalline structure when you expose them to air or you heat them. They become anhydrous. Why are they anhydrous? Water have moved out of them. They are now anhydrous, no water. And they are what? Powdery. They will lose weight. They will lose their shape as well. Right? Beautiful. If you get that very quickly with me, on exposure to air, what do we say will happen to it? A good example is your sodium trioxocarbonate for what? Decahydrate. It will lose that white crystalline structure. It will lose water, it will lose everything. Look at it now, it is losing 9 molecules of the water, right, as vapor. And then it will now turn to what? Your white powder. Instead of it to be dehydrated, it's now what? Monohydrate. Another example very quickly is your blue crystals of your copper 2 tetraoxosulfate what? Pentahydrate. It will lose all the 5 molecules of water attached to it on heating. When you heat it, what will happen? It will form your what? Your white powder copper 2 tetraoxosulfate what? 6 at the end of the day. All these guys are what? Efflorescence. If you get that very quickly now, you are sure you understand it. Answer this question for me, question 45. But please, question 45, we'll begin it in the next class. That is your part 5B. I'll see you there very quickly. No time to waste. I'll see you there for the now. Bye. This class you just finished watching, of course, is brought to you by what? By the LearnLift app. Oh yes. And within the LearnLift app, you have access to all your classes from the beginning to the end. Everything is well organized for you. Every singular subject, every singular topic followed in line directly with your syllabus and your curriculum. And of course, can I tell you something lovely about the LearnLift app? Oh, this is the sweet part of it. You have access to your Jamb classes within the LearnLift app. You have access to your WAEC, your NECO, your GC classes. You have access to your post-UTME classes. And that's not all. Of course, for your secondary school, you have access to your secondary school classes, whether SS1, SS2, SS3. You have access to your classes directly. And of course, if you're in the university, you have access to your 100 level as well as 200 level classes, all within the LearnLift app. And of course, your 200 level classes are for medical students. All of them are there, well structured and highly organized for you. But please, before you proceed, just head down to your Play Store or your App Store and just type what? LearnLift. Immediately you type LearnLift, of course, the app is going to pop up for you and you download the app and then you start learning immediately. And also very quickly, all you're going to do is that in the description of this video or in the comment section, just open it. You see the link to our WhatsApp channel. Click on it and you are in the WhatsApp channel already, where I'm going to be dropping information every blessed day on a regular basis. And also very important, if you want to reach out to LearnLift, this is LearnLift contact, any of the two, right? Just copy it down and then WhatsApp us, right? Either you send WhatsApp message or you put a call across to us and all of that, and we're going to attend to you immediately. Guess what? I'll see you in the next chapter. For the now, peace out. Bye.